Hi, good afternoon, everyone. Oh, sorry. Hey, can you hear me?
Yes, we can hear you. A little bit of noise, but we can hear you.
I'm sorry, I'm stuck at the airport. I've been waiting here for the last 5 hours to give this presentation.
Okay, so we can hear you.
Yeah, I might be now.
Mhm.
Yeah, my name is Kanting Motimele. I'm an MSc student at the University of Western Cape. The work I'm going to be presenting here is part of my MSc research, where I looked at relativistic mean field theory and mm, proton-induced reaction of bit unstable nuclei with inverse kinematics, in particular the exclusive P2P reactions. Mm, in the past few years, there's been a big development in the production of unstable nuclei. So we decided that maybe we should try to answer some questions that have not not been able to have not been answered conclusively with stable beams with stable nuclear targets. So we decided to study the medium modification of unstable nuclei with inverse kinematics using the P2P knockout reactions. The choice for the P2P reaction was motivated by the fact that this approach is ideal for studying scattering process containing essential physics and has been successful since 1952 to study single particle properties of.
Kanting, can you just show your presentation in full screen, please?
Oh, sorry, let me do that.
Yeah, much better. Thank you.
Okay, thank you. Mm, this kind of reactions are also best suited to study the nuclear medium, and the P2P reaction remains one of the most important one of the most important mechanism to study exotic nuclear. In the direct kinematics, this kind of reactions proceed by um, incident proton interacting with the bound proton in a target nucleus in the final channel. The experiment is set up in such a way that the two outgoing protons are detected in coincidence with each other, and the residual nucleus and the residual nucleus is normally not detected. However, in the inverse kinematics, the rules of the projectile and the target are reversed. The nucleus of interest is used as a projectile, and the proton is used as a target. In the final kinematics, the detection is still the same. However, since we are going to be looking at the medium modification, we need to look at exclusive P2P reactions. In the exclusive P2P reactions, in the case of direct kinematics, the incident proton is polarized, and the two outgoing protons are also polarized. In the inverse kinematics, the target proton is polarized, and similarly, the two outgoing protons are polarized. As a matter of fact, RIKEN facility in Japan has been able to produce polarized proton targets. So we were inspired by that. The reason we studied this, we believe that in future it will be possible to measure the complete set of spin observable of exclusive P2P. Now, in order to gain any facts from this kind of reactions, we need to have some simplify assumptions. In our case, we have two important assumptions. First is that the collision time is short, and second is that before the collision, there's no interaction between the incident proton and the target incident proton and the target nucleus in the direct kinematics. And additionally, in the final channel, the two protons don't interact with each other, and they also don't interact with the residual nucleus. This gives rise to plane wave impulse approximation, in which the wave functions for the incident proton and scattered nucleons can be presented by plane waves. The approximation is sketched below like this. You see that we have the wave function. The wave function of the incident proton in the initial nuclear state that carries information about the incoming proton, and then we also have the bound state wave function of the bound state wave function carry information about the bound proton in the target nucleus. I need to add that in our case, the bound state wave function was developed with relativistic mean field theory using FSU Gold parameter set. The latest parameter set, FSU Gold parameter sets. Then in the final nuclear state, we have the wave functions of the outgoing particles, the scattered proton and the ejected proton. We see that the residual nucleus is not involved. The nucleons of the residual nucleus are not involved. They do not interact with the outgoing protons. The scattering process is contained in the invariant transition matrix. Here we start the process where we include the distortions. But since we are going to be using relativistic plane wave impulse approximation, we remove the distortions to have our transition matrix made of the plane Dirac spinors and the bound state wave function now in momentum space. The bound state wave function can be written as a two-component vector containing the upper bound state wave function and the lower containing the upper wave function in momentum space and the lower wave function in momentum spaces also. These wave functions give momentum distribution of the states from which the bound proton of interest is in. In our case, we looked at S1/2. That's where this is the state where we ejected the proton from different doubly magic oxygen nuclei. And here we can see the evolution of the momentum distributions, and you can see that they are dominant, they are significant around 150 MeV. Then now, in order to calculate the spin observables or polarization transfer observables, we also need to mention that the reason we use plane wave approximation is because, generally speaking, polarization transfer observables are insensitive to distortions. They are often described as the ratio of spin-dependent cross sections. This is the T matrix that we calculated above that carries our information about the scattering process. Then we found this. Using the inverse kinematics, we plotted the spin observables. We see that these observables analyzing power and polarization, they distinguish different oxygen isotopes. This implies that there may be medium modification. It recognizes the medium effects as the number of neutrons are added in oxygen nucleus. There's some change according to this in the nuclear medium. This is consistent with some predictions that have been made that there may be nuclear modifications in the nucleus. However, when we look at the rest of the spin observable, we see that there's no the background won't be okay because I'm at the airport. So we see that the predictions for these observables are the same, meaning that there's no significant medium modification as you add the number of protons. This happened to be the case for different kinematical conditions that we looked at. So from this study, we concluded that same as with the stable isotopes, we cannot say conclusively that there is any medium modification in the nucleus. Now summary conclusions. We conclude that only 3 of 7 spin observables distinguish between different oxygen isotopes. We cannot conclude on the existence of medium effects based on these results. The reason we use the polarization observables or spin observables of exclusive P2P is because they carry rich information about the fundamental physics of this process, and they are far more effective discriminators of subtle dynamics than the unpolarized cross sections. The rationale is that they are not sensitive to distortion effects. And finally, in practical terms, ignore distortion results in enormous simplification, since we can use trace methods to do the calculations. Thank you for listening. Any questions?
What are you doing at the airport, Kanting?
I'm going home. I'm going home.
Can I just ask? So you've ignored any predictions on the unpolarized triple differential cross sections for this particular reaction? Wouldn't that also be an interesting observable to look at in order to extract spectroscopic information about the particular nucleus?
No, if we were to look at the unpolarized cross sections, we will need to include distortions because these distortions are important in unpolarized cross sections. It do not have served the purpose of looking at the medium modifications. The spin observables are far much better discriminators.
Okay, thank you.
Okay, I was saying, I think I was muted, so I was saying that thank you for your talk and thank you for doing the effort of doing the presentation and in the airport. So we have another question in the chat. I think so. Gregory Hillhouse asks, how does your model do for stable nuclei?
For stable nuclei, it works. It works as well as it works as well. We tried it for stable and unstable, except that with the stable we have to use direct kinematics, and the T matrix also has to be different.
Good. More questions or comments for Kanting?
Let him going home because
Yeah, I think so. We don't want you to miss the flight. So thank you very much again, Kanting. And since it's the last talk of the session and the morning session,
I also would like to thank Prof. Lindsay for the practice that we did, for the practice sessions that we had together. I'm really thankful for that. I think it has really made this an interesting thing.
But did you thank your supervisor at Stellenbosch, Brandon van der Ventel?
Oh, and
he's been the key player here.
Yes, he's the one who
I would like. This is a beautiful case of Kanting is registered at UWC, but he has Brandon van der Ventel from Stellenbosch University as the main supervisor. Thank you, Kanting.
Yes, may you please send me the video so that I can share it with him as well.
We will. Thank you.
Thank you.
Okay, so as I said, thank you very much for all the speakers of the session. And so I think, so I give the word again to the organizers. And so thank you again, and I will clap for everybody.
Thank you, Tomas. Thank you so much for being in such a long discussion.